Okay, thank you. Welcome, everybody. First talk of the day. Everybody is well awake after the cheese and wine. And Julian, Andreas, Klode is going to present us new stuff about APT, who is working on for, I don't know, more than 10 years, I think. Yeah. Thank you so much.
So, hello, everyone. I wanted to talk a bit about the new APT solver I'm working on, and a bit of the history. We're going to have about 3 sections and questions after each section, so we don't need to do all the questions at the end. So the current solver started 26 years ago in the original APT and has been developed ever since. It's more or less grown over time in sort of an ad hoc fashion. Whenever we had a problem that we needed to fix, we fixed it, and it's quite unwieldy to read. And it often leads to a bit of wrong results. So this is an example here from Ubuntu that I generated earlier this year, where we actually have 3 versions of apt available. Apt only has this concept of a single candidate version. So in this case, it will pick the candidate version is the one from the PPA at the top, and then you have the version in the proposed, oracular proposed in the middle, and there's an older version that's the oracular release version. That we want to downgrade to in the second command. And we can see the problem that instead of downgrading apt and reverse dependencies, what actually happens is that apt utils depends on the same version of apt, and it is being removed. And not only is apt utils being removed, but Ubuntu minimal also depends on apt utils. So that's a meta package. And it removes that meta package, and it also removes other stuff depending on apt utils, which is sbuild and auto package test, which is not really what we want. What we would really like to see would be either not downgrading because of dependencies, or downgrading everything that's needed. And for a completely stupid reason, apparently it also upgrades the libraries to the version from the PPA, which makes no sense because it's completely unrelated and in the opposite direction. There are a bunch of other issues like this where it removes packages that it shouldn't remove, and installs packages that it doesn't need to install because it tried to upgrade a package and didn't upgrade the package, and the install request was still being kept. But I think most of you will have probably seen those issues themselves. So another issue you've probably seen is when you're running the install command, a lot of time will be spent on the building dependency tree phase. Surprisingly, I was benchmarking this on a Raspberry Pi, and on the Raspberry Pi, building dependency trees was actually not that slow. But on the Intel machines I was having, or the AMD machines, we spent about 40 to 45% of our runtime building that dependency tree. It's just this little function on the bottom left. It's build dep cache. So what happens is that it actually traverses all the dependencies in the archive and checks everyone if it's satisfied or not, which is just an enormous waste of time, which worked, I guess, 26 years ago because there weren't a lot of packages and even much less dependencies in the archive. But these days, things are way too complicated to do with every dependency in the archive. And the new solver, we can see on the right, the new solver, total runtime is 15% in this example. And that's about the same runtime as the old solver adds on top of its setup. So essentially, the left tree will fall away once we can completely switch over to the new solver. So we'll see a runtime improvement of, I guess, 40%. Which will be nice. And yeah, getting back to the example, what actually we can see now with the new solver, if we run it, is that by default, it will actually deny the downgrade request because it introduces a new policy and to keep manually installed packages installed. So in this case, Ubuntu Minimal was a manually installed package, and we can see that if we were to downgrade apt, we would need to remove apt utils. And we can see that it says unsatisfiable dependency. Ubuntu Minimal depends on apt utils. And then there should be a but somewhere. Oh yeah, none of these versions are considered of apt utils because the selection of apt that we made prevents the selection of the version of apt utils that are valid. So the error messages are still a bit in the early state. They completely need some revamping to be nicer to read. There will be multi-line messages instead of the short notation there. But the interesting thing is we can now introduce a new feature, which is no strict pinning, which disables that single candidate behavior. And now apt will consider all the versions available for the package. So in this case, it will downgrade apt utils and not remove any packages anymore. And that's not entirely done yet, right? The solver is not entirely done in regards to source packages, so it should be downgrading the entire source package in the end. Currently, it's only downgrading the packages that it needs to downgrade. And other features are going to be an apt-y command. So the apt-y command is slightly different from the one in aptitude because it actually dumps you the solver state. So it traces the solver, the path the solver took to install the package, which will be essentially the shortest path to the package. But it doesn't work with 2 arguments, and we don't have a why not command right now. I haven't figured out how to write a why not command. Let's call it that. Apt install fix policy is an existing command that you can use to switch to make the system more aligned with a new install. That can, of course, now be a bit more optimal because we can now essentially tell the solver to ignore all the automatically installed packages, and then it essentially will pick every package as if only the manually installed packages were installed, which means that when you run the command, you will essentially get the same set of installed packages as everyone else that would do a fresh install of the same set of manually installed packages. And in the same vein, apt auto remove can be made more extreme, I would say. So some of you might have noticed that you collect a lot of version GCC packages over the years. And the culprit seems to be that libtool depends on GCC or C compiler, and each version GCC package provides the C compiler. So now apt currently keeps all the version GCC packages installed because of the alternate choice here in the dependency where it says GCC or C compiler, which is a bit suboptimal, let's call it that. But it is certainly the safest choice to make. And now we can keep only the latest only the strongest path installed, which in this case would be the GCC choice in the org group. Yeah, that's the first section. The next section would be the history of how we got there. But do we have any questions so far?
I have one.
Wait.
So you mentioned the no strict pinning, considering all the versions and not only the one with the highest priority, but also ignoring the fact that some packages are manually installed. Aren't those 2 separate things, like no strict pinning acting also as a ignore manual flag? So am I right that there are 2 things that flag does and not only one?
I think that's a misconception. That's the fix policy option that would make it ignore all the automatically installed packages. And the no strict pinning option is a completely separate option from that.
Thanks.
Okay. Then I guess let's move on to history. So I've been working on this in my free time already for about on and off since 2010. When I think people first started working on set solvers for packages in like 2007 or 2008. OpenSUSE did the libsolve stuff. And my first attempt at this was to use an external set solver, so you can translate the dependency problem into a set problem, which is the satisfiability problem. So you translate your dependencies to the conjunctive normal form, they call it, which essentially is a list of ends of OR groups, essentially. And you have these literals, they can be positive or negative. So if you have dependency A depends X or Y, you translate it to not A or X or Y. And if you have an A conflicts X, you have a not A or not X. And you can pass that to an external dependency solver. So in 2010, I was using PicoSet. PicoSet apparently is also what FreeBSD's package turns out to be using. The problem with using an external set solver is that we have only limited ways to tweak its behavior. In case of PicoSet, essentially for each variable we can say the default guess should be 1 or 0, but there were no really other options to configure how it searches for solutions, so it might find solutions that are correct, but not the solutions we actually want. And also this does not support recommends, because it only is a basic satisfiability problem and doesn't install as many packages as possible, essentially. So you can increase that you can improve that with PseudoBian optimization or other forms of more complex problems. I chose PseudoBian optimization, which is fairly similar, but it also adds an optimization function, and the constraints are translated a bit differently. Notably, we can compact all the conflicts of a package into a single clause. And I think the math is correct, but I didn't check the paper that I was using back then. But essentially, then you specify global optimization criteria, such as the number of removed packages, the number of changed packages, or the number of packages that will be newly installed, or the number of packages that are not up to date. Then you can lexicographically combine those, or use another way to combine them to get an optimal result, or to get the optimization function that you want to minimize or maximize. And I implemented 2 early versions of this with Clasp. So the first one was in 2012, which was a Python script that translates the problem to a text notation of a PBO. And the second one in 2018 was calling the Clasp library internally. And then I wrote another one in 2021, which was using the Z3 theorem proof from Microsoft Research. The Z3, all of them had problems because the Clasp one was not really a package as a library, and Z3 also adds, I think, about 8 megabytes or something to the. It's an 8 megabyte library or something like that, so it adds a lot of install size. And the problem with optimizing globally in general is that it can have surprising results, because we're used to this greediness of the old app solver where it picks the first choice in a dependency. The PseudoBian optimization solvers, they will work completely different, because they only respect the optimization criteria. So we had, for example, the Plasma desktop had a search tool, and it had multiple backends. And one of those backends was, the preferred backend was, I think, MySQL back then. And there was an alternative SQLite backend. And if you run one of those solvers on that problem, it would install the SQLite backend, because the SQLite backend involves fewer packages, which was very surprising and not at all what we wanted. And of course, it is hard. There's a hard performance trade-off due to the global optimization, because the performance is fairly driven by the global optimization criteria. So if you specify the wrong criterion first, it will completely lead the solver astray, and it will try to do something very weird and might not actually complete in any reasonable time. So that was not optimal either. I tried hard to make it more greedy and improve the whole thing, such that it behaves more like the old app solver, but didn't really get anywhere, and it felt a bit wrong in the end. So attempt 3 was not ever implemented, but I think it was a way of me getting more I want to say, considering the dependency problem as a different kind of problem. In this case, I was looking at it as a graph, and then each node in the graph can contain one or more packages, and you can have edges between those nodes, and the edges would split essentially for the OR groups, so that you can go this way, you can go that way, or you can go that way. And then you can provide a bunch of primitives to optimize that graph. So you can replace an edge that leads to one set of packages with another edge that leads to a smaller set of packages. You can eliminate cycles by merging the nodes together. So if A depends on B and B depends on A, you can replace the nodes A and B with a node A and B. And yeah, nodes with a single parent get merged into the parent. There were a couple more primitives. You can look at the wiki page if you want to find out more. And then you have the most important primitives, I would say, are the branching primitives, where essentially you find the smallest edge and pick a choice. And then if that choice didn't work out, you go back and eliminate that choice from the edge, such that you are left with a smaller problem. But as I said, it was never implemented. It was back in 2021 as well. But I think it led to the idea a bit of the new solver, which is actually, the idea was fairly trivial. We start by putting all our dependencies into a priority queue. We order that priority queue by the number of choices that we have, such that the dependencies with the fewest choices come first, and if there's a dependency that doesn't have any choice anymore, that will obviously be the first one. Then you have dependencies that only have a single choice, so you need to install that choice. And then you will have more and more choices to make. And each time we make a choice, we need to bump a level variable. It's called the decision level. And then we can say, oh, that package will be installed, that package should be installed. Or we can say that package should not be installed at all because something conflicts with it. And we store that categorization together with the level such that we can backtrack if that didn't work out. So we can try to install a package. If that fails, we go back. Then we can try another package, and so on. Now, some of you might have noticed this actually does look like a set solver to some extent. It is not fully a DPLL set solver. It's more halfway between a naive solver and a DPLL solver. So in case you're wondering what is a DPLL solver, so a DPLL algorithm sort of is a divide and conquer approach to the set problem, where you perform two important additions to the naive solver, which is unit propagation and pure lateral elimination. And then you do the usual, you pick a literal, you set it to true, or you set it to true, you try if that leads to a solution, and if that doesn't lead to a solution, you set it to false and see if that leads to a solution, which I would say is sort of a divide and conquer approach. Unit propagation means that a clause that only has a single unassigned literal, so in our case that would be a dependency that only has a single package left that can be installed to satisfy it, such a clause is called unit. And if we see a unit clause, we pick the literal that is unassigned and assign it in a way that the clause becomes true. So in a case of a dependency, we install that dependency. In case of a conflict, we would reject that package. Now, we have that partially because we're ordering our dependencies by the number of possible choices. These unit clauses come first, so we have some sort of unit propagation, but it's not entirely complete because we are looking at the dependencies lazily. Once we have picked a choice, we actually only look at the dependencies for that choice, and we don't store the conflicts after we of these packages ahead of time. So we can't propagate units backwards. So if you have A depends on B, depends on C, conflicts with X, and you install X, and then you later try to install A, you don't yet know that A is not installable, despite you should know that it's not installable. If you have full unit propagations, you would have seen when you install X, you would have marked C as not installable because it conflicts with X, and then you would have marked B as not installable because it depends on C, and then you would have marked A not installable because it depends on B. And yeah, we don't have that yet fully. We might get to it soon. And the other thing was pure literal elimination. So that means if a literal appears only in the same polarity, so it's either not A or A, entirely in the formula, then we can always set it to true, but it doesn't necessarily make sense for us because essentially it means we install a package that nothing conflicts with, and we don't install a package that has no dependencies. So pure literal elimination doesn't make sense for package dependency solving. And yeah, that's the history so far in the background. And the next thing we would discuss is the current and further work. But maybe someone has questions right now. Okay, then we move on. So this solver is quite powerful, or it's going to be quite powerful. So we want to restrict it a bit to not pick solutions that actually don't make a lot of sense. So for example, manually installed packages should not switch architectures. So if you remove foo on AMD64, you're shipping at foo and i386 installed just because you have multi-arch configured. Or the same with conflicts. If something conflicts with foo AMD64, we shouldn't install foo i386 as an alternative, but remove the package that conflicts with foo AMD64. And as I said earlier, manually installed packages can only be removed explicitly. What does that mean? One option of explicit removal is essentially if you pass the package to be removed as an argument to apt when running apt. And the other thing would be if you have a package that replaces it. Actually, conflict replaces and provides it. That package essentially is a designated replacement package, which is what happens currently with the time t transition, where you have libfoo1 t64 conflict replaces provides libfoo1. For example, you should be able to remove libfoo1 despite being manual to install libfoo1 t64. And yeah, there are a bunch of details in there. I don't think we need to go through them, but if you want to read them, you can read them in the slides afterwards. And as I mentioned, we also require a single candidate version by default, so no strict pinning is not the default behavior. That makes it more predictable, and it narrows the search space a lot, because now for each package we only have to consider one or at most two versions. In case it is installed, you have the installed version and the upgradable version. And you can control more of this. So I like to call this structure-guided solving, because essentially we have this dependency list and we always pick the leftmost choice in the OR group. So what we can do is we can change the order of choices. What we did in the old solver, we already was, for example, we moved the installed package first in the choice. So that if you have A or B or C and C is installed, we reorder this to C, A, or B, such that we try C first before we try A or B. And in the same vein, we can reorder obsolete packages to the last, to the end of the OR group. And obsolete packages here is defined a bit more loosely than maybe in other contexts. So one definition of obsolete was the package is no longer in the repository. That works most of the time, but it turns out that if you have old binary packages stuck in the archive and a newer source package uploaded, you should also consider those obsolete. So if we see for the same source package new binaries for the same architecture, then that package is also obsolete, which improves our ability to upgrade in terms of inconsistent archive states. It's like in between unstable states where, for example, we have the libfoo1 to libfoo1 t64 transition, and libfoo1 is still in the archive. We should still consider it obsolete and try to upgrade to libfoo1 t64 instead of trying to stick with libfoo1. Because the archive keeps libfoo1 around until every reverse dependency of it is rebuilt against libfoo1 t64, and we don't want to wait on this necessarily to upgrade your system. And we can also change the order of actions itself, so the order of dependencies. And actually, the manual installs and automatic install requests are ordered with those together. So what I did is I ordered the dependencies before the manual installs and then the automatic installs at the end. Because essentially, as I said, the backtracking is chronological. So once we go back, we will first try to undo all the automatically installed packages before we ever go back to trying to undo a manually installed package, which will also allow us to allow you to remove manually installed packages with the new solver, and it will still behave in a reasonable manner, because it will only try to remove a manually installed package if there's no solution that involves removing an automatically installed package. And yeah, satisfying dependencies with only new packages first and satisfying dependencies with obsolete packages last is kind of the same thing we did with changing the order of choices. So our libfoo1t64 dependency will get solved before a dependency on libfoo1, which essentially is equivalent to a libfoo1 or libfoo1t64 dependency. So we need to look at the libfoo1t64 dependency first, such that we see the new package first. We install the new package, and then when we get to the dependency on the old package, we will see, oh, this dependency is already satisfied by the new package, and move on. And in the same way, we order the obsolete packages last. So libfoo1 or libfoo1t64, it contains the obsolete package libfoo1. It would get ordered to the end, in the hope that, of course, we find another solution first that solves that problem for us and that we don't have to look at the obsolete package at all. Now, there is some more further work to be done on improving the unit propagation, they call it. So I was looking at the Miniset paper, which is like the basic set solver paper that everyone is looking at, that writes set solvers for package managers. And there are some practices we don't yet quite use, which is the conflict-driven clause learning. The conflict-driven clause learning is very important because it avoids us re-entering the same conflict multiple times. You can imagine something depends on something, and eventually end up in like a conflicting cluster at the end. And then you have another path that eventually leads to the same cluster. And with conflict-driven clause learning, you can essentially jump back to the root level that actually introduces the conflict and then cut it off, and we don't ever get to explore the same conflict again, which I think hopefully will solve my test case that I have, which is a Mantic to Noble upgrade from Ubuntu, which currently doesn't yield a result. It just runs endlessly. Or it might yield a result, but it doesn't yield a result in like an hour or so, so that isn't very helpful. And I see in the log output it always has the same conflict in the end, so that would help a lot. And the other thing that makes things a bit faster is to watch literals. So when you look at these clauses, you actually only need to watch two of the variables in them. So if you have A or B or C, imagine you have A or B or C. What happens is that if you assign A, you pick two watchers, let's say A or B. You assign A. Now you change the watcher for A to C. Now you assign C. Only B will be left, so you have a unit clause. If you assign B, only C will be left, and you have a unit clause. And yeah, this way is much faster, because what we currently do is even worse than what classical set solvers do. So classical set solvers essentially record for each clause all the variables that they contain. It's called the occurrence list, and then when they assign a variable, they look at all the clauses that contain these variables and then check if the clause is still satisfiable. What we do is way, way worse than this, because we basically look at all the clauses right now and check if the clause contains the variable in the first place, and then if it has changed by the assignment, which is super slow, but avoids having to worry about any optimization so far. So it actually works reasonably well in terms of performance for us because we don't do a lot of backtracking. But it is way silly, so let's not do it. The Miniset paper and the state-of-the-art sat solvers, they have a couple of practices that don't make sense, like they count the activity of clauses and then they remove some clauses that they learned, and they do restarting the solver after I think unlearning the clauses, deleting the clauses, and that generates some sort of non-deterministic behavior. As I said earlier, if we have an A or B dependency, we always want to install A if possible. And classic sat solvers don't care about the shape of the solution, but more or less they only care about if the problem is solvable in the first place. And we actually care about how the solution looks. So we can't use everything that a sat solver, that the state-of-the-art sat solvers do. As we already saw earlier in the presentation when I was referring to the pure literal elimination, where essentially we install every package that doesn't have a conflict. And yeah, so when do we want to roll this out? And we actually have the early alpha available, which is what I was talking about earlier. So before the further work slide, that's in the archive right now in app 2.9 point something. You can specify the ---- solver 3.0 argument to use it. If you specify the no strict pinning argument, the 3.0 solver will be enabled automatically for you because the old solver doesn't support no strict pinning. But it will give you a warning saying that, oh, the new solver is now activated. And yeah, in about February or Trixie, we want to have it production ready. More or less as a beta, like an opt-in beta, so you can still use the solver 3.0 argument, but the default solver will still be the old one. Then we want to test this a bit in Ubuntu, make it the default in Ubuntu first. Do some like automatic regression reporting and analysis and see what breaks and what we need to fix. And then once Trixie is released, we want to make it the default in Debian as well. And yeah, that's it, everyone. Thank you. Any questions?
Excuse me, but is there any quotation papers with regards to what you talked about the sat solvers?
You can look at the Minisat paper. I haven't linked it, but I can add it to the slides after the talk, and then you can look at that at least. I'm trying to write a sort of paper on the new solver itself, but I haven't written that yet.
Then where's the slides available? I'm curious to check out after this.
The what?
The slides you mentioned here.
Yes, they should be linked from the DebConf talk page, I think.
Okay, thank you.
Is it possible to verify the correctness of your solver without having to run it in production, I guess you could say? Like, is it in your last slide you showed that you're going to be trying it out in a future Ubuntu version. Is there a reason why it can't be proven correct without like production trials?
So I think the first step is I want to try to enable running the solver in addition to the old solver in the background with like a time limit, and then we can report feedback from that. But we actually deploy that to everyone such that all the systems can report feedback. But you still use the old the result of the old solver. You don't have to trust the new solver, so we run the new solver, and we check if it reports a worse result, and then we report it to some central analysis server.
So I'm kind of new to, I've been using Debian for a long time, but it's just worked for me but I've noticed some of these things, I would agree that objectively there are superior ways of doing them, but a few of the slides and a few of the options you pointed out, I feel like that somebody might have an opinion on maybe saying, oh no, I want to have, this other preference. And so are you, of course there's ways to hold packages and all those classic ways. But I'm talking about a more meta way of saying, oh no, for this system I prefer something a little bit more ephemeral of some nature, and say I want you to solve it this way. Ignore what your personal preferences are.
Yeah, I think there's going to be some way to configure some more preferences into the solver. Like the obsolete handling, for example, that I showed, you can disable that to not order obsolete packages less and then run with that. So I try to make it a bit modular in the way that you can disable some policies and enable other policies and play around with it.
Thanks for working on this. Can you talk some more about how other distributions do this? Like, do they have similar challenges? Do they solve it better? Like, when you're done with this, you're going to be doing this better than everyone else and all that?
Yeah, I mean, most of the RPM distributions use libsolve, which is a version of Minisat that was developed by SUSE, like 2007, I think. I find it a bit weird because it implements its own cache format and it implements its own package file parsing, essentially. So I did not try to use that. And APK has its own solver, so Alpine's APK tool has its own solver, which I was looking at as an inspiration. I think we have gone a bit further into the direction of stat solvers than APK has. And FreeBSD, I was mentioning, has the package tool, which uses picosat apparently. Yeah, I don't know what what other distributions are doing.
Do they have similar challenges? Do they have similar challenges? I mean, are you solving problems they have also?
Maybe. Like, for example, the A or B behavior that we have in Debian, in RPM, I think it is implemented differently. So in RPM, I think instead of saying A or B to indicate a preference for A, you say A or B and then recommends A. So it's less order dependent possibly in other distributions than we are, because we've gotten used to a greedy solver for 26 years and they did not. All right. I guess that's it.